So in this video, we're going to take a more thorough examination of causal reasoning. And in doing so, we're going to look at 5 methods that John Stuart Mill had developed in being able to identify causal interactions. So these are methods that help us track when there is a genuine causal relationship obtaining. And before we get to those methods, we should talk about the word cause and how it's used in English. So the word cause is actually ambiguous in English, and there's 3 different senses in which we can mean by the word cause. We can mean sufficient conditions. So for instance, if I say taking a swim will cause us to cool off, what I'm saying is that's sufficient, that suffices for us to cool off. If you swim, you're going to cool off. Of course, I'm not saying that it's a necessary condition. There's other ways to cool off besides swimming. You can have a cool treat like a snow cone or ice cream. You can go sit in some air conditioning or go sit in the shade, etc. But one of the ways in which you can cool off is to go swim. So swimming causes you to cool off. But we can also mean by the word cause necessary condition. So for instance, sprinkling water on the flowers is a requirement for it to grow. So we will say that sprinkling water on the flowers will cause them to grow, but we don't mean that it's sufficient, that it's enough to guarantee that the flowers will grow. And that's because there's all sorts of other things that go into flowers growing. So we need sunlight, we need the nutrients from soil, etc. So in this case, when we're using the word cause, we must be picking out a requirement or a necessary condition. And then there's even cases where we use the word cause to pick out a condition that is both necessary and sufficient for another condition. So for instance, you can't get an increase in electrical current unless you have an increase of voltage, and vice versa. And if you have an increase in voltage, you will get an increase in electrical current, and if you get an increase in electrical current, you will get an increase in voltage. So in this case, when I'm saying an increase in voltage causes an increase in electrical current, I mean it in the stronger sense of necessary and sufficient conditions. So let's review more thoroughly just what we mean by sufficient condition, necessary condition, and necessary sufficient condition. So we say A is a sufficient condition for B in cases in which A's occurrence guarantees B's occurrence. That is, if A, then B, you get A, you're going to get B. So examples, if Bob is a lizard, then Bob is going to turn out that Bob is a reptile. So being a lizard is sufficient. It guarantees that you're a reptile. If Bob is a parrot, then Bob's going to be a bird. Being a parrot guarantees that you're a bird. So that's what we mean by a sufficient condition. Necessary condition, on the other hand, is a requirement. So getting the condition isn't going to guarantee that you have the other condition, but if you don't have a necessary condition for something obtaining, then you won't get that thing. So A is a necessary condition for B in cases in which B's occurrences requires A to have occurred. So since A would be a requirement for B, if you don't get A, there's no way that you got B. If it turns out that Bob is not a reptile, there's no way Bob can be a lizard. If it turns out that Bob is not a bird, then there's no way for Bob to be a parrot. So if not A, then not B, or if B, then A. And then there are necessary and sufficient conditions. And we say A is a necessary and sufficient condition for B in cases in which A's occurrence guarantees B's occurrence and B's occurrence requires A to have occurred. So basically we have the conditional running in both directions. It's a combination of if A, then B, and if B, then A. In fact, the way that we'll oftentimes state necessary conditions is A occurs if and only if B occurs. If and only if. That's supposed to be picking out both of the directions of the conditional. So for example, we have an increase of heat if we have an increase in molecular motion. But not only that, if we don't have molecular motion, we won't have an increase in heat. And if we increase the molecular motion, we will get an increase in heat. And if we don't have an increase in heat, there's no way to have an increase in molecular motion. So the increasing heat is a necessary and sufficient condition for increasing molecular motion. Likewise, and this has the same meaning, we have an increase in molecular motion if and only if we have an increase in heat. Okay, with that under our belts, let's take a turn. Let's now turn our attention to looking at the 5 Mills methods. The first method that we're going to look at is the method of agreement. And what we're doing in a method of agreement is we're trying to figure out what we're trying to identify necessary conditions for a phenomenon. So we're looking for the cause of a phenomenon in the sense of a necessary condition. And to build evidence for this, then, what we need is several of occurrences in which the phenomenon happens. So let P be the phenomenon. So we need several occurrences in which the phenomenon happens. And then we have a group of other sorts of conditions that we want to know whether they're a requirement for the phenomenon or not. So notice that as A keeps occurring with B, there's a good chance it seems that A might be a necessary condition, but if A is missing in just one case, it can't be that A is required for P. Because if A is required for P, then any time that we have the phenomenon, like we do have it here, you better have it here as well, but we don't. In this case, we do not have it. But, so if B doesn't have it here, then we don't even need to proceed going on. We know that it's not going to be a necessary condition for P. And if it's missed in just one case, even in multiple cases, we know that D is not going to be our necessary condition. But if in every single case C occurs, that's very strong evidence, not perfect evidence, of course, it's probabilistic reasoning, but it's very strong evidence that C causes P, that C causes our phenomenon in the sense of being a necessary condition. All right, so let's look at method of difference. Our method of difference is a systematic search for a cause that is a sufficient condition. So what we're trying to do is identify a condition that seems to guarantee the phenomenon. In the method of difference, we're only going to see 2 cases instead of the several cases that we saw before. And for the phenomenon in question, it'll always occur in one of the cases, either in 1 or 2, but not show up in the other case. And then we'll have our several conditions. So let's say it's A, B, C, and D. And the point is, there'll be only one difference between the conditions that we suspect to be a cause of the phenomenon. And what's important is that on case 2, A, B, and D all appear when the phenomenon didn't. It cannot be the case that A suffices or guarantees P, that B suffices or guarantees P, or that D suffices or guarantees P if they occur but P fails to occur, right? They fail to guarantee that P occurs if P doesn't occur when they do. So that tells us that A can't be a sufficient condition, tells us that B can't be a sufficient condition, and D can't be a sufficient condition. They all got falsified. The only condition that doesn't get falsified here is C. So this is probabilistic evidence that C is a sufficient condition for P, for our phenomenon. The third method is the joint method. And what we're trying to do with the joint method is find a condition that is both necessary and sufficient. Now, even though that's ideal, that's what we're hoping to find. We're hoping to find a cause that is both necessary and sufficient for the phenomenon. This method can find a condition that's merely a necessary condition, and it can find one that's merely a sufficient condition. And basically what we're doing in the joint method is we're employing tactics that are very similar to the method of agreement and the method of difference. So it's not true exactly in saying that we're using both of those methods combined, but the strategies that we are combining are very similar to those strategies. So in order to employ the joint method, we need multiple cases. So 1 case, 2 case, 3 case, 4, maybe 5 cases, maybe more. And our phenomenon is going to occur in some of those cases, but not other ones. And now we can judge, for instance, A, whether it's a necessary condition. And we can go through each of these by thinking that first whether they're necessary conditions. By seeing if every time that we have a phenomenon, this condition obtains. We don't in this fifth case. Right? The phenomenon occurred without this. So there's no way for this to be a necessary condition. There's no way for it to be a necessary condition. B automatically, because we don't have it in our first case, but we have the phenomenon, can't be a necessary condition. C very well, or C is going to end up being necessary condition, because every time P occurs, so does C. Doesn't matter that C occurs here, because we're not worried at this point whether C is a sufficient condition for P, whether it guarantees P. We just want to know whether it's required. You can have requirements, things that are required for a phenomenon and not the phenomenon, but you can't have the phenomenon without its requirements. Automatically, D is not going to be a necessary condition given the first case, and E we're not going to let be a necessary condition either. And then suppose, now that we've looked through necessary conditions, we need to check for sufficient conditions. So we want to see if the occurrence of one will guarantee the occurrence of P. Let's modify A a little bit and say that we do have an X here. In which case, in the third case, it didn't guarantee P. So it's not a sufficient condition. And let's, in this fourth case, let's have B show up so that it's not a sufficient condition. Well, C is not going to be a sufficient condition either because of 3. In fact, let's have both E and D on the fourth case show up, in which case we didn't have a sufficient condition. All we have is, and all that we can learn from this is that C is a necessary condition for P. But let's modify this a little bit. So let's say that really we didn't get C here. Then notice that each time that C occurs are times that P occurs, and each time that C doesn't occur are times in which P doesn't occur. Well, if you're both a necessary and sufficient condition of a phenomenon, then you'll occur at all the very same times, because the occurrence of one is going to guarantee the other, and you can't have one without the other. So that would mean not only is C a necessary condition, but if we modified the case as I just did, it would turn out that C is both a necessary and sufficient condition. And there will even be cases in which you can find sufficient conditions but not necessary conditions. All right, before turning to the fourth method and the fifth method, middle methods, let's take a look at the examples implying these first 3 methods. All right, so we've got a chart here that's going to tell us something about a phenomenon and various conditions that we think might be associated with the phenomenon. So let's say that the phenomenon, just to make this more concrete for you, let's say the phenomenon was that you got some sort of a skin rash. And you think to yourself, well, what might be the cause of this skin rash? Maybe it's your detergent. So that'll be condition A. Maybe it's your bathing soap. Maybe it's your deodorant. Maybe it's from when you are gardening, some plant that you're allergic to when gardening. And maybe it's some medication that you're taking that you have an allergic reaction to. And you think, well, these all seem like the likely causes of having this rash. And so you chart out, you think about when all of these occurred and when the phenomenon occurred. And you're asking yourself, well, what is the cause of this phenomenon? The first thing to ask yourself, given this chart, is what kind of method are we employing? Is this a method of agreement? Is this a method of difference? Or is this the joint method? And it's going to be the method of agreement because we have several cases, we have several instances. 1, 2, 3, 4, 5, 6. And not only that, but our phenomenon occurs in each case. And so we're looking for falsification, and the only way we can get falsification in this case is if we're looking at necessary conditions. So we ask ourselves, is A necessary for the phenomenon to occur? Well, on Tuesday and on Friday, we had the rash, but we weren't wearing clothes that we used our particular deodorant on. So that can't be it. Monday, Tuesday, and Wednesday, we failed to take a shower, I guess. So we didn't use we didn't bathe, we didn't use our soap. So B was absent even though we had the phenomenon. So it can't be a requirement to have the phenomenon. At least we wore deodorant on the 3 days that we didn't bathe. And we forgot to wear deodorant, luckily, at least on one of the days that we bathed. But still, since it's absent in the case on Saturday, and we still got the rash on Saturday, it can't be that the deodorant is a necessary condition. Can't be a plant from the garden. But this medication that we take every single day does occur every single time that we have the phenomenon. So probably E is a necessary condition. It is the cause of the rash as a necessary condition. It has to be present in order for us to have the rash. So this is method of agreement. One quicker strategy than what I've gave you here for method of agreement is to see that we have multiple instances where the phenomenon occurs each time, and we find the case that completely agrees with it, that is, also occurs each time. And what we can find with these are necessary conditions. Let's take a look at the next example. All right, so now we have this other chart. Notice in this case we don't have a bunch of cases. We've only got 2. And that's a strong indication that what we're dealing with here is the method of difference. And because we need cases of falsification, we're trying to rule out other conditions. And because the method of difference looks for sufficient conditions, what we do is we look to see when the phenomenon doesn't occur, yet when our other conditions do occur. Because if E occurs in our second case, but we don't get our phenomenon, E can't be a sufficient condition because E failed to guarantee the phenomenon. Same with D. D fails to guarantee the phenomenon. B fails to guarantee the phenomenon. A fails to guarantee the phenomenon. So the fact that we don't have a case in which C fails to guarantee the phenomenon, that's evidence that C is a sufficient condition. So this is the method of difference. And methods of differences allow us to find sufficient conditions by ruling out the other conditions that fail to guarantee the phenomenon. Let's take a look at this third chart. If we examine the phenomenon column, then what we'll see is that we have several instances, 7 cases, and many of those cases we have the phenomenon occurring. But in many of those cases, we don't have the phenomenon occurring. Well, since we have several cases, it can't be that this is the method of difference, because the method of difference only has 2 instances, 2 cases. And because the phenomenon doesn't occur in each of those cases, all 7 of them, it can't be the method of agreement. So what we're dealing with here is the joint method. And in the joint method, what we're hoping to find is a necessary and sufficient condition for the phenomenon. But it can turn out that we only find a necessary condition or only find a sufficient condition. And the way that we determine whether we have a necessary condition or sufficient condition is by ruling them out as possibilities. So let's say we start by ruling out necessary conditions. Then what we do is we start, just like in the joint method, we start by looking at the cases, like we do with the method of agreement, we start by looking at the cases in which the phenomenon occur, but the condition in question doesn't. So the phenomenon occurs in case 1, but it doesn't for A. That means A can't be a necessary condition. We look at B, and in fact, each case in which the phenomenon occurs we see that B also occurs. So we don't get to rule B out. But we do get to rule C out. And we do get to rule D out. and we do get to rule E out. Of course, all you need is one case in which the condition doesn't occur, but the phenomenon does, to show that it's not a requirement. There can be several cases, as there are in these examples, but once you find one, you know it's not it. All right, so what we've shown then is that B, we've got some evidence that B is a necessary condition. And we know that A, C, D, and E are not necessary conditions. So now we want to determine whether any of A, B, C, D, and E, if they're sufficient conditions. And in order for a condition to be sufficient, any time the condition appears, it's got to be the case that the phenomenon appears as well. So if we want to, we're always checking in terms of falsification. So then what we do is we look, instead of the cases in which the phenomenon does occur, we look at the instances in which it doesn't occur. And since A does occur, but the phenomenon doesn't on instance 2, on case 2, A cannot be a sufficient condition. B failed to guarantee, as just like A, fails to guarantee the phenomenon on condition 2. So even though it's a necessary condition, it can't be a sufficient condition. Same with C, can't be a sufficient condition. D can't be a sufficient condition, because on 5 we get D, but it failed to guarantee that the phenomenon occurred on case 5. E can't be a sufficient condition. So even though we were employing the joint method, and we were hoping to find a condition that is both necessary and sufficient, all we can determine is that B is a necessary condition. So B is necessary for the phenomenon. So let's look at the fourth method, the method of residues. And what we're doing with method of residues is we separate from a group of causally connected conditions and phenomena those strands of causal connections that are already known, thereby leaving, which is why it's called residue, the required connection as what's left over. That must be what's explaining the leftover phenomenon that is occurring. All right, so let's step back and talk about what this means. The underlying idea is that there can be several causes to one phenomenon. For instance, there might be a draft. You might notice a draft as you're sitting in your room, and maybe it's uncomfortable, and you identify plausible candidates for this, whether there's an open window, the ceiling fan's on, right, just as two examples. And then suppose you turn off the ceiling fan and it reduces the draft, but there still is a draft. Well, okay, there still needs to be a leftover explanation. So then you close the window and that reduces the draft, yet there still is a draft. Well, there's this residue that still needs an explanation, and then you think to yourself, well, it's got to be coming from underneath the gap of the door. The door has a gap of from the floor, and there's some air from outside that's making its way and causes draft. Then you head over there, and sure enough, you can feel the wind coming out from underneath it, and then when you block that, no more draft. So the idea is there can be several causes that are related to a phenomenon. If you start accounting for some of those causes or all of those causes but one, then that can help you find out what the remainder cause is, and not only that, but to what degree it has a causal impact on the phenomenon in question. Let's look at another example. So if our phenomenon is that enrollment is down and we want to identify why the enrollment is down, well, you might do some statistical analysis and find out that say 30% can be explained from the fact that we're in a recession, so the economy is bad. People just can't afford it. 30% can be 30% can be explained by an increase in tuition. So again, people can't afford it because you've increased the tuition. And there's still this remaining 40%. Well, how is that going to be explained? Oh, well, it must be because people are now looking at certificates that you can get much cheaper than getting a bachelor degree, for instance. And it must be that people are deciding to go for these certificates instead of a bachelor degree. And that's what explains this remaining 40% drop in enrollment. The last method that we'll be looking at, the fifth Mill method, is the method of concomitant variation. And the idea here is that we find two conditions that have a correlation with each other. Now, of course, correlation doesn't equal causation, but if there is causation, there will be a correlation between things. So it is some evidence. And we increase that evidence by toying or changing one of the correlates, one of the things that are being correlated. So if we mess around with one of them and then we see that that has an effect on the other, then that suggests that there is a causal relationship. Again, it's not going to be perfect evidence, but it's some evidence that there is some sort of effect going on when you mess around with one of the things being correlated. So, for example, when Jennifer studied, she noticed her test scores went up. So there's this positive correlation between Jennifer studying and her test scores going up. Now, that's not enough to say that studying causes her test scores to go up. But if we mess around then with the condition of studying, so we take an instance in which she doesn't study, and then we notice that her test scores go down, now we see, now what we're finding is it looks like there's an effect here. It's not just a correlation, but there's a causal relation. So it's appropriate then to conclude that there's likely a causal connection between the two. And of course, if we repeat this type of experiment again and again and again, and we keep getting the same result, then we're acquiring more and more evidence that there's a causal connection and that it's not just happenstance. Since the method of concomitant variation lies at looking at correlates and how they are correlated, and if we vary one of the correlates, whether that has an effect on the other correlate, we need to talk about correlation more generally. So here we have a graph, and on our graph we'll have what's supposed to be a y-axis. Let's try that again. There we go. and we have an x-axis, and as we move up on the y-axis, one of our conditions is increasing, one of our correlates is increasing, and as we move to the right on our graph, then one of our other correlates is increasing, like in terms of frequency or amount, etc. And as we move to the left, one of the correlates is going to be decreasing, and as we move down, one of the correlates is going to be decreasing. So we can ask ourselves, if we see a pattern where our correlates are correlated in the following way, we want to know, well, do we have a positive correlation here? Do we have a negative one? And if so, is it highly, weakly, or perfect? So the answer in this case is D. Our correlates are correlated highly in the negative sense. And that's because as one of the correlates increases, we see a pattern in which the other correlate decreases. If they were to both be increasing, that'd be in the positive sense. But since one decreases when the other one increases, they're correlated in the negative sense. So a positive correlation then would look like this. And for it to be perfectly correlated, you would have each, so that, imagine that is supposed to be a perfect line that goes right through there and doesn't have any of these waves because I can't draw a perfect line. If the instances of the dots were right on, I know these are a little off because I can't get them right on, but if they were right on these and there wasn't a change at all, then it would be a perfect correlation. If it looked, let me erase this. So what we can take away with that is the tighter knit, the closer that those dots occur, the higher our correlation is. And if they're more spread out, then here we still have a positive correlation, but it's pretty weak. It's a pretty weak positive correlation. So far, the kinds of examples that we have seen throughout this video are the kinds of, or representative of the kinds of questions that you might have to answer on your homework and on the quiz. But you might also have to answer a question like this. So 5 students at Vernon Elementary School become nauseated shortly after lunch. The school nurse makes a list of what each student had for lunch and notices that each of the 5 had tuna salad. From this observation, the nurse concludes that the tuna salad caused the students nausea. Which method did the nurse use in drawing this conclusion? So we have to think to ourselves, if we were to draw a chart out and we're talking about other things besides tuna salad, what is that chart going to look like? Well, there's going to be several cases. There's going to be several cases in which the phenomenon happens every single time. That is, they get nauseated every single time. And the phenomenon occurs every single time. those are all standard characteristics of the method of agreement, which means the method that we used is the method of agreement. And the only type of cause that our method of agreement can show is that of a necessary condition. So in order to have gotten nauseated from the school lunch, you had to have eaten this tuna salad.